Hey folks, Todd Coburn here with your Aerospace Structures series. This lecture is on bending of solid and lumped sections. So as we get started, it's good to remind ourselves of where we've been and what we know. We know that if we have a cross section subjected to an axial load, we're going to get a uniform distribution of stress, as long as we're far enough away from the point of application, equal to P over A. If we examine any little element on the cross section, we will see that it all experiences that average stress level, P over A. That's a normal stress because that stress is perpendicular to the area. Now, if we have a force that is parallel to the cross section, we're going to find the same kind of idea. We will find a stress that's basically can be assumed to be constant across the section. So for any little element we looked at, we're going to get that same shear stress, P over A. If we have torsion on a cross section, we will also get a stress distribution going from 0 at the centroid to the maximum value at the extreme fiber. It's going to be TR over J, torque, distance to the point, which is the radius, where it's maximum at the outer radius, divided by the torsional constant J, which happens to be the polar moment of inertia for a round section. Once again, this is a shear stress since the force is parallel to the cross-sectional area. Today we're going to learn about bending and the stresses that bending causes. When we have a bending moment on a section such as the one you see here, we're going to get a distribution of stress. That moment is going to cause forces to act on the cross section, which is going to drive stresses. The stress is going to vary from 0 at the centroid to a maximum value. In fact, you can look at it from the one tip of it, the extreme fiber on the bottom, to the extreme fiber on the top. And for this kind of bending moment, which would be positive bending moment for beam sign convention, we're going to see we go from a positive tension at the very bottom to a maximum compression at the very top, where the stress distribution and the strain distribution are linear from bottom to top. And if we take a look at any little point on the section, we're going to see where that stress is going to be a function of its position relative to the centroid of the neutral axis. This is what we're going to be studying today and investigating how those stresses are calculated. If we look at a common beam that's subjected to pure bending, now normally when we have bending, what we're going to have is a shear force, and the further we get from the point of application of the shear force, the more bending that develops in the beam. But if you take that shear force out through a reaction, you can end up with bending moment that's still carried in the beam, and we get a condition which is called pure bending because the beam is in bending and there's no shear anymore. Most of the principles we're going to apply today will apply whether we have shear or not, but it simplifies things somewhat to say this is pure bending with no shear. So if we look at this bending moment that's going to bend this beam in a smiley face fashion, you can see if you put ink on your hand and you smack it on the right end of the beam and then smack it down on the page, you can see what this cross section is going to look like. Or if you want to take any section cut, you can do the same thing. Chop your hand into the beam with the ink on the palm of your hand and then rotate your hand out and smack it on the page. And that's exactly how that section will look using third angle projection. So we've got this bending moment. We can imagine we're going to get stresses going from a positive value at the bottom to a negative value at the top. As we do apply this bending moment, we're going to end up bending this beam. You can see that this beam gets bent into a curved surface. For example, do I have a nice little flexible? Here we go. So if we bend this with a bending moment like this, you can see it's bending into smiley face bending. That's a common terminology when we're doing bending analysis. You'll notice as we bend it, there's a deflection of the beam. We've got a bending moment applied. Later we'll look at the deflections of the beam. Today we're going to look just at the bending stresses that develop. You can see when this beam is straight, you could say that it has an infinite radius of curvature. But as we bend the beam, there's now a finite radius of curvature, which gets smaller and smaller. The radius from the beam's arced shape to the center of curvature gets smaller and smaller as we bend into a tighter and tighter radius. And we're going to look at that radius of curvature. We're going to look at the bending shape of the beam. We're going to look at the idea that at some surface, as this beam deflects, there's going to be a neutral surface that gets no deflection. We're going to pretend that plane sections remain plane, such that our strain distribution is linear, and the stress distribution is correspondingly linear if we have an isotropic beam, a homogeneous beam. So we're getting this bending. So we can imagine this surface. There's a surface somewhere within the beam that doesn't get longer or shorter as we go into the shape. That's called the neutral axis. Not longer or shorter, and the stress we're going to find right on that neutral axis is going to be 0. Then you'll notice as that cross-section rotates, you can see that on the inner surface of the beam, it's actually getting shorter as this beam rotates, which means it's going into compression. All of that part of the beam is in compression. On the outer surface of the beam as we rotate, that part is stretching longer and longer. We can look at that a little tiny strip on the extreme fiber. We see that's getting longer by some amount. We're going to focus on these strains and these deflections. So we can see there's a middle surface that does not deflect. It deflects, but it doesn't get longer. The inner surface gets shorter and the outer surface gets longer. And this is the things that are going to be happening and we're going to be investigating. We can look at the length of the beam. We're going to look at like a half length. You see there's a L here from end to end of this beam. But in this little lower picture where we're bending the beam, I'm going to redefine L. I'm going to call LO. So we could say like the half length of the beam as we go into this curvature. And you can imagine that while that was flat here, as we curve, that thing is the middle surface is going to have that same distance, LO, from the middle to that point. But out here on the outer surface, since that one's getting longer, it's going to be a little longer than LO. And on the inner surface, it's going to be a little shorter than LO. This is the principles we're going to be looking at in the following slides. So if we consider that straight beam, and now we're bending that beam into this shape, we're going to focus here on a few things. We see that the strain, remember strain is just deflection over original length. So if you look at the outer surface of the beam, the lowermost fiber of the beam from the center to the end, we call that length LO. And when we bend, that's going to get longer, and it's going to get deflection because it's getting longer. And if we divide that deflection by the original length, that's the strain. The same time on the inner surface, we look at this, that outer surface is getting longer and longer as we're bending. That inner surface is getting shorter and shorter. So we take the original length, we see it's getting shorter. That deflection divided by the original length is the strain. On the inner surface, it's going to be a negative strain. On the outer surface, a positive strain. So strain is simply the deflection divided by the length. It can be positive or negative. Now, if we take a closer look at the deflection of this beam, let's take a look at this little triangle here going from the center of curvature to the neutral axis, running along the neutral axis and then back up. We can draw this little thing. So where this R is the distance from the center of curvature of the beam to the neutral surface of the beam. And that length was not changing. That little length L is still L because it's not getting longer or shorter. We're saying the beam pivots around that point, gets shorter above it, and gets longer below it. So we can see that there's a relationship between the R and the L. S equals R theta, right, for small angles. We also see, if we look at the little triangle, we see a little outer triangle working from B at the neutral axis out to B and B prime. And we see that that little part is getting, if we focus right here, we see this little part here is like this. And right up here, we've got a little part that's like this. We see this little deflection is getting smaller. This is negative. And this little deflection here is getting a little larger. We see that if we that all of our measurements, we're going to define from this neutral surface, we're going to define y as moving toward the center of curvature from this neutral surface. Therefore, a positive y moving this way gives us a negative strain, and a negative y, as you see here, moving from the neutral surface outward, is going to give us a positive strain, because this part, this thing was original length here, and now when you wrap it around and stretch it, it's now longer than it was. This arc length S is a little larger than LO. It's LO plus whatever the deflection is. And these deflections are looking flat, but actually they're running along the beam like this. Meanwhile, this one was some distance R, and now it's getting, or LO, and now it's getting a little shorter up here, because we have this surface, which now is bent like this. So on the inside, it gets a little shorter. On the outside, it gets a little longer, such that it ends up in a shape like this. Pivoting about this point, that's this much shorter, and this is this much longer. And this length divided by, this deflection divided by that length is the strain out here on the outer surface, and this deflection divided by this length is the strain on the inner surface. That's what we're focusing on here. And we're going to see in a moment there's a relationship between this triangle, which is this triangle, and this little triangle right here. Okay, so we're going to focus on that next. So we can see here that the deflection relative to the negative y, this is called negative y because remember y was positive, assumed to be positive, moving from the neutral surface toward the center of curvature. Therefore, if we're on a point down below toward the outside of the beam where it's bending, that's going to be a negative y. So this deflection divided by the negative y is equal to the length original divided by the radius of curvature. That's just a trig relation. We can rewrite that in this form, delta over L equals negative y over r. Okay, so stay tuned. Oh, one more idea. We can also remember then, if we put this together with our strain relation, we find out we can write the strain as simply negative y over r. So if we're above the neutral surface, we're going to have a negative strain. Positive y means a negative strain. Negative y means a positive strain according to this. Okay? So looking at this is our way we're bending our beam in this positive smiley face bending now, and we're going to continue our derivation. We're going to focus on the force on any elemental strip. So as we deform, we're developing stresses on the beam. Since we're squeezing it, we're getting a strain, and the strain is related to the stress. If you just imagine we've got a rectangular section, and we break it up into, say, 8 slices. 1, 2, 3, 4, 5, 6, 7, 8 uniform slices, as you see here. We're going to get a stress distribution that's linear going across this section from inner surface to outer surface. We just focus on 2 strips. If we call them 1 at the top and 8 at the bottom, we're going to focus on the stress on strip 2 and on strip 8, just for purposes of study. We see there's a stress distribution along here, but if we look just at one strip, we see on the second strip, our stress is sigma 2, and on the last strip, our stress is sigma 8. On sigma 2, it's in compression. On sigma 8, it's in tension. So if you understand that, we can say, well, the force on that strip is just the stress times that little unit area, which is just the width times whatever that little delta H is. The moment is whatever that force is multiplied by the y. Remember, y is defined as positive from the neutral surface moving toward the upper part of the beam. So if we're up at the upper surface, we're like, if the beam is h tall, it's h over 2, positive h over 2. If we're on the outer surface of the beam, it's negative h over 2. We can write the bending moment, if we call this bending moment positive, that gave us a smiley face bending. This is called beam sign convention. We can see the inner surface is in compression, the outer surface is in tension. The force on strip number 2 is causing a moment about the neutral surface, and the moment is just the force, which was just the stress times the area, times the distance, which is just the distance from the neutral surface to the center of that strip, which I'm identifying as y2. Notice that y2 goes from the neutral surface to the middle of that strip. The force times that is the little moment contribution of that strip about the neutral axis. We can write that same moment for each and every strip. We can write the stress in strip 1 times its y distance plus the force stressed in slice 2 times its area, which is a force, times its y distance from the neutral surface, and so on. The moment on each strip is given here. The total moment then will be summing all of those together, the moments on every strip, which is the stress on every strip times the area on every strip, which makes the force, times the y distance from the neutral surface. If our moments are in the elastic range, then we have Hooke's law, stress equals modulus times strain. If we combine that with our strain relation, we can say that the stress is actually negative of the E times Y over R. Now, R is kind of a nebulous, arbitrary number, or arbitrary, kind of hard to understand number. We can imagine how that works in terms of our deflection. It's hard to put our fingers on because it's so far out there for most bending deflections. But we're going to remove that shortly. It's suffice it to say that our stress is related to the modulus stiffness, the Young's modulus of the material, times the distance y over r, because that talks about how far that is from that pivot point. Remember, we're pivoting about the neutral surface, which doesn't get larger. So if we're in here, we're getting a negative stress, negative strain, and the magnitude is going to be y over r multiplied by that E. Y over r, and the stiffer the material, the more stress it will develop. If we're down below the neutral surface, that means we're going to have a negative y, which we're going to have a negative negative. That's going to give us a positive stress, and that fits our assumption as well. If we insert this into our total moment and rearrange this puppy, we can calculate the total moment, just the summation of the E of each strip times the area of each strip times the y of each strip squared over the r. Now, we're not going to use this formula yet. We're going to keep modifying it until it becomes something simpler, so stick with me. Picking up where we left off, we developed this equation, and now we're ready to note that this ay squared term is just the moment of inertia. So if we want to calculate that separately, we can just change that out with the I, which is the moment of inertia. Since we've got bending about a horizontal axis, that's going to need moment of inertia about the same horizontal axis. And we see that the m over I is equal to the E over R. Okay? If we combine that with this stress relation, we can rearrange this puppy. We can write that the stress is equal to the negative of the total moment divided by the total moment of inertia times the y, where y is defined from the neutral surface moving toward the center of curvature. Now we're going to use y and x for a lot of things in identifying our section. We're often going to define our y from a different point. So you got to be really careful using this. When we have this equation derived this way, when we're saying the stress is equal to negative my over I, what we're saying is you have the total moment on the section. You have the total I of the section about the same axis. And now you're going to multiply by the distance from the neutral surface to the point, pointing positive as being toward the center of curvature. And then you're going to have this negative sign in the equation, which means if you're above that point, you're going to get a compression stress. If you're below that point, you're going to get a tension stress. Okay? This is foundational, and we can write it like this again, just to be clear. M is the moment on the total section. Y is the distance above the neutral surface, and I is the moment of inertia of the total section. The moment is bending about a certain axis, in this case a horizontal axis, and the moment of inertia needs to be calculated about the same axis. Often we'll write this in a different form. Stress equals MC over I. A lot of folks in industry will just say stress equals MC over I. What they're saying is M over I times the distance to whatever point you want the stress. And usually they're looking at the stresses at the extreme fiber because that's where the stresses are maximum. So when we say stress is MC over I and we leave off a positive or negative sign, what we're saying is it's the moment divided by the I times the C value, the distance from the neutral axis, and we're going to have to make sure we insert the appropriate sign, and often this is done through intuition. We can see if we're talking a beam that's square and it's 5 inches tall, then C that we're interested in for maximum stresses will be plus and minus 2.5. 2.5, if you put in a minus 2.5, you're actually going to get the stress up at the top where it's in compression. If you get a positive 2.5 on there, that's going to be the bottom stress. So whether we use My over I or MC over I, it's the same enchilada. Okay? We're going to do that less this semester, but when we get into structures 2, we will be learning about plastic bending. It will be important to be able to talk about the moment carrying capability of the beam is as a function of moment rather than stress. And in that case, we can start laying the groundwork for that by just inserting FTU for our stress and then solving for the allowable corresponding moment. This would be an ultimate moment from this equation written this way. Okay? So when we're dealing with elastic bending, we have some assumptions we've been applying in using this equation. We're assuming that plane sections remain plane or not distorted. The length of the longitudinal axis at the neutral axis remains unchanged. Everything's rotating about that point. Plane sections remain perpendicular to the longitudinal axis. In-plane distortion is negligible. The material behaves in a linear elastic fashion such that Hooke's law applies. And the entire section has the same modulus of elasticity. Now, next class, we will learn to deal with multiple materials in our cross section, but today we're going to focus on a single material. So at this point, it's good to talk about, it's very common, so we're used to dealing with the right-hand rule for all sign convention. That's a very positive tool that's very useful. However, when we deal with beams subjected to lateral loads, such as we see in houses and things, it's very common to use beam sign convention, which is defined as smiley face bending. You see, as this beam is bending, it's going into smiley face bending. If it's going into smiley face bending, then it is a positive bending moment. This is a positive beam sign convention because of smiley face bending. This is a negative beam sign convention because it's a frowny face moment. See the difference? Smiley face, frowny face. Make sure you understand that. That may be different than right-hand rule sign convention. We're going to see why now. So if we look at this smiley face bending, you'll notice that this smiley face bending is causing compression on the upper surface. If you look at figure 614A, you see the bending moment that's shown is causing compression on the upper surface. You'll notice that the fingertips are tapping down on the section. That means there's compression there. And the palm is pulling away from the page. That's going to be tension there. That is positive beam sign convention. Now, when we deal with the vertical axis, if we had a bending moment about a vertical axis, you'll see that there's no smiley face because it is just about a vertical axis. It doesn't look like a smiley face at all. So for that, we will always use right-hand rule for a vertical moment, which means if the thumb is sticking up the positive axis, then it's a positive moment. Okay? If we had used right-hand rule, you'll notice here that we have our sign convention defined here. We have the X and the Y. These are located from the neutral axis of the beam, right? X and Y from the neutral axis of the beam. If this is the centroid, this is the bending moment about which that occurs. In this case, the neutral axis of the beam is here. In this case, the neutral axis of the beam is here. We're seeing compression on this part. We're seeing compression over here. Okay? This is beam sign convention. You'll notice if this had been right-hand rule, we would have called, since the x-axis is here going that way, this would have been a positive moment for right-hand rule. But for beam sign convention, but that drives a frowny face bending in our case. Smiley face bending gives us a positive moment. Beam sign convention says the other direction is positive. So if we're saying the moment is this moment here is positive because we're using beam sign convention. If we use right-hand rule, that means we're going to draw our x, y, z coordinate system, and a moment is called positive if it has got their thumb jammed up the rear end of the positive axis. Positive x-axis, positive y-axis, positive z-axis. In that case is bending, which is negative beam sign convention. You got y bending, and you've got a torque on this puppy. Okay? So if we deal with this guy, you'll notice here again, just to drive this idea home, remember when we use that formula in the manner we've shown it now, my over I or mc over I, what we're saying is it's the moment on the total section, it is the I about the same x-axis, and we also have the y position of the point where y is defined as positive from the neutral axis. In this case, the neutral axis and CG are the same. Okay? We're going to actually leave this nomenclature moving from the neutral surface, and we're going to do something a little more detailed in just a moment. But if you understand this concept of mc over I, where c is just the distance from the neutral axis, that will be a useful tool in analyzing these problems. To take this a step further, let's look at this beam here. We can see now that we have defined our coordinate axis in a more natural fashion. Usually what we'll do is we'll sketch our cross-section and whatever it looks like. So you'll see we sketched our cross-section like this. And once we sketch it, we'll want to dimension that puppy. And once we do that, we want to define our coordinate system. I recommend we start from the lower left corner. Moving to the right, we'll call that x. Moving up, we'll call that y. Now you'll notice y is no longer defined from the neutral surface. So in order to calculate our stress, we're going to need to first find the neutral axis and then calculate the distance from it. And that means that sets us up to write these equations. So if we want to use beam sign convention for calculating stresses, then we use m about the x, where m is defined as positive if it causes compression on the top. In that case, it's a bending moment like this, times y minus y bar over I. Now what this is just m about this horizontal axis, centroidal axis. This is I about the horizontal centroidal axis. And then we're going to calculate y minus y bar. What that means is, let's say we want the stress right here. You'll notice the position of that from our origin is y. Now this is a different y than we had when we started this lecture. This is the y from this coordinate system. But what we need in this formula is y defined from the neutral axis. We say y minus y bar, that is this distance here, and that's the distance we need. So actually this is a more general form that we can use. Anytime our moment is defined with beam sign convention, we can use this formula to calculate the stress. What that means is, remember beam sign convention, compression on top. If we are looking for the stress at a point up here, that I just means at some point I, let's say it's this point here, we're going to put in the position of that point y minus y bar of the section. We have a negative sign here. That means if the point is above the neutral axis, this term is positive, this is a negative sign, and that's going to make our stress negative as we expect. If our y is down here, then y minus y bar is negative, and those two negatives cancel, which means it's going to give us a positive stress. So we can use this form of the equation anytime we have beam sign, if our moment is defined in beam sign convention. Now, if our moment is defined in right-hand rule sign convention, then we will then say, then that means positive moment is like this, and then we will just turn that leading sign to positive. And therefore, a positive bending moment will cause our stresses to have the right sign. So if we have our moment defined in beam sign convention, we will use this form of the equation. If it's in right-hand rule, we use this form of the equation. Got it? Okay. Let's look at bending about different axes. So we've been talking about bending about a horizontal axis like this. Okay? If we're using right-hand rule sign convention, this is our equation, which means we can just plug in yi is the distance. You'll notice our coordinate system is defined from this point. There's positive x. This is positive y. So if we want the stress at point C, we would just put in the y position of C, which is actually big H, minus y bar of the section, which in this case would be h over 2, divided by the I of the section about the centroidal x-axis, which is 1/12 bh cubed. And that will give us the stress at that point. If instead we want the stress at point A, we would put in the position of A, which is just 0, minus y bar, which is h over 2. Our I is still 1/12 bh cubed, and that gives us the stress there. If we want the stress at E, at the centroid, then y is at h over 2. Y bar is still at h over 2. That means the stress is 0. Because our stress distribution on this puppy is going to be linear, going from a maximum stress here is F equals mc over I. This C is now h over 2, to F here, which is negative mh over 2 over I. It's a linear stress distribution. It's a linear strain distribution. We can calculate the stress in here. We can calculate the stress right here. All we would do is in this equation, we would plug in the y position of this point and subtract the y bar and divide by the I multiplied by the m. If we want the stress right here, we just put the y position of that point in this equation. We can calculate it about any point. Okay? All right. Now if we have bending about a vertical axis, my, now we're going to use this form of the equation. Using right-hand rule, we've got a positive moment, has your thumb jammed up the rear end of the y-axis, where the y-axis is at the centroidal thing. Once again, you'll notice our coordinate system is springing from the lower left corner. And now our stress is going to be m times x minus x bar over I, and it's going to be negative of all that. What this means is, if we have a point that is to the right, if we have a point like, for example, point C has an x value of b, and we can see by inspection our x bar is just at b over 2. So this quantity is b minus b over 2. It's a positive value. Our moment divided by the moment of inertia about that axis, this is just 1/12. And now, because we're talking about bending about this axis, so it's 1/12 hb cubed. And we have a negative sign because if we're any point over here has this quantity positive, and it's going to drive a negative stress. So this negative sign takes care of that. If our point had been here, which means we have this value, like let's say we talk about the stress right here, that's going to be 0 minus b over 2. This quantity is now negative, multiplied by this negative gives us a positive stress over to the left of the neutral surface, which is correct. That's how we do a vertical stress. If we have bending about both axes, we've got mx and my. We simply add these two equations together, and the summation of those gives us the stress. The one is going to get a linear stress distribution about one axis and then a linear stress distribution around the other. If we had bending about two axes and an axial load, we will simply superimpose the P over A stresses on top of our bending stresses, one about the x-axis, one about the y-axis. And that's going to give us the total stress. What this means is we just plug in, if we want the stress at any point, like let's say here, we just say, well, point C is at point B, comma, H in terms of this coordinate system. We plug those two values into these equations. B goes here, H goes here, and that solves for the stress at that point. If instead we want the stress at point A, we would have put in 0 for X, and we would have put in 0 for Y, and that would have given us the stress at that point. That's how it works. Okay, now if we have, now you'll notice this looks nearly identical, but you notice this coordinate system here, this is called Y, and this is called Z. So the same basic form of the equations apply, but now we've got the moment about the Y being resisted by the I about the Y, and now what we're going to need is the Z minus Z bar term here with a positive sign, the moment about the Z divided by the I about the C, and then we're going to have the Y minus Y bar term with a negative sign, and that will give us the appropriate stress in the normal direction. Got it? Okay. So those are our basic concepts. Now we're ready to start getting down to the nitty-gritty where we're actually computing these stresses. So let's look at a method for calculating bending, 1D bending, which means bending about one axis. First, we're going to sketch the section. For example, if we had an I section, we would start out, or a Z, let's say it's a J section, we'd start out by carefully sketching the section, and it would also make sense to dimension the section. So we dimension the section, let's say this is 1 inch, and let's say this is 5 inches. Let's say this is 0.1 inch. Let's say this is 0.1 inch. Let's say this is 0.2 inches. Let's say this is 2 inches. Looks like we're fully dimensioned. We're also, you'll notice in our next step, we are going to define our coordinate system. We're going to start from the lower left corner, so we'll call that positive X. We'll call this positive Y. That's what we're going to use to define where everything's at. Okay. Next, what we're going to do is we're going to idealize our section. So for this guy, what that means is we're going to break it up into little bite-sized rectangular chunks. So we can just divide it up here. We'll call this element 1. When I'm doing this, we're going to construct a table in a minute, and the table is going to work from top to bottom, and it's good to number your section the same way from top to bottom. So we'll call that 1. We'll break this up here. We'll say that's 2, and we'll call that 3. And later we can talk about the width and the height of each element and the x, y coordinate of the center of each element. That's what we're going to be learning how to do momentarily. Okay? We're now ready to idealize our section like I just showed you. And this shows you some other idealizations for different kinds of sections. If we have an angle or a T or a hat section, we will break it into little elements and then number them so that we're ready to construct our table of properties. We then construct our table of properties, and what we're going to do is we're going to list first the, we'll number however many, 1, 2, 3. In this example, we have 2 elements. There'll be 2 elements in our table. This example has 3 elements. This example has 5 elements. We'd have 5 things. Our I section had 3. Got it? What we're going to do next is we're going to say, okay, we're going to put into that let's say that we're doing this section right here. And let's say this was 2 inches. Let's say this is 3 inches and everything is 0.1. That means element 1 is 2 inches wide and it is 0.1 inches tall. And it's located at, from here to the midplane is going to be at 3 minus half of that thickness, which is 2.95 is the y position of the middle of that. Element 2 is 0.1 inches wide, and it is, looks like it's 3 minus 0.1, which is 2.9 inches tall, and its y bar is going to be 2.9 divided by 2. We then calculate the area, which is just this times this, and the area of this. We take the area for this column, we take the area and multiply by that y bar. We then sum this column, and we sum this column, and we divide this by this, and that gives us the y bar of the section. That tells us where the y bar is relative to our coordinate system. Remember, if this was our section that we did, and we called this our coordinate system, then our y bar is going to be defined like this. Okay? If we sum this column, that column is actually our area. Great. And now we're ready to start calculating the bending properties. So we'll now take the, let me clean this up a little bit. That means we would take, to calculate this column here, we're going to take the area of each, multiply by the y minus y bar squared, and write that here. Then we take the area times the y minus y bar squared, put that here. There were only two elements in this, so that's the only part of the table we're using. We sum up this column. And we also, that's the moment of inertia due to these areas not being at the centroid of the section. Then we calculate the moment of inertia of each of these areas about their own axes. So that's going to be for this element, it's going to be, this is going to be 1/12 bh cubed. That goes here. The second one is going to be 1/12 bh cubed. That goes here. Those are our only two terms. We add these together. Our total moment of inertia is going to be this column summed with this column. And that we put that summation right there. That's the I. We now have all the properties, and we say, well, we're going to have to worry about the stresses. If we have a bending moment like this, we're going to need the stresses up here. It's going to be M times y minus y bar over I. This is an M about the x and an I about the x. And now, if we're using right-hand rule sign convention, that would be a negative. So if you have a point up here, that will give you a negative stress. That is our stress at any point. That is how we do it for solid sections with bending about one axis. If we had had bending about a vertical axis, we would have then constructed our properties about the x-axis instead of about the y-axis. You'll see this in a minute in our 2D section properties. Next, we identify our points for max potential stress, and we can apply our formula like this. This is a little example showing the same thing. This is going to be a slightly different order of steps, but the same thing applies. We're idealizing our section. Let's say we have a rectangular section. We could break it up into 2 pieces, construct our table. We notice we have the widths and the heights. This particular element looks like it's 1 inch wide by 4 inches tall. That gives those. We then calculate this column. We calculate this column. We calculate our A and our y bar. Then we calculate this column. We calculate this column. We calculate our I by adding those 2 terms. That's the area. This is the y bar. Then we calculate the I by adding these 2 columns together. We then go and we look at what is our loading and what points will be critical for bending wherever our y is greatest, and we can calculate our stresses at those points. See how that works? Okay. Now if we have a section that looks scary, all we have to do is lay out our table and put in each width, each height, each y bar, and then calculate once we've broken it up into strips. This is a typical frame section. This is a typical eye section. Both of these are commonly encountered, and you can do it by just constructing a simple table like this. Now, if we have two-dimensional bending, then we will calculate a table for both properties. We do everything the same way, only this time you'll notice we have our B and our H, and now we're going to call out both the X bar and the Y bar. What that means is, for example, if this guy is 1 inch wide and 2 inches tall and 0.1 inches typically thick, and this guy is 2 inches wide and 4 inches tall and 0.1 inches thick, and this guy is 2 inches tall, and this is 2 inches, and this is 1 inch, and everything's 0.1 inch, then we could use this guy. Well, we'd end up with two terms. We'd have our element 1 would be 0.1 by 2.0 with an X bar of 0.05, a Y bar of 1.0. Our second element is 1 minus the thickness of the other, which means it's 0.9 wide. It is 0.1 tall. Its X bar is at, you'll notice here, we look at this closer, our X bar is 0.1 plus 0.9 over 2, which means 0.45 plus 0.0 plus 0.1, which is 0.55. Our Y bar of element 2 is going to be at 0.05. Once we have that, we calculate this, calculate this, calculate that, put it there. Calculate this, calculate this, calculate this. Take this divided by this and put it there. Then we calculate this, which is A times Y. Calculate this, calculate this. Now we calculate our centroid. This over this gives us our Y bar. We now can calculate our area Y minus Y bar. Area times Y minus Y bar squared. And our area times Y minus Y bar squared. Sum up these columns. Calculate our moment of inertia about the x-axis. This is 112 BH cubed. Sum those up. Now you add these two terms together, and that gets you your bending about the x-axis. We take our area times the x minus x bar squared. Add those up. Calculate our bending about the vertical axis is 112 HB cubed of each element. Sum those up, and this plus this is now our moment of inertia about the y-axis. We can then use this equation, or for bending about two axes, that triple equation where we have P over A and MC over I about both axes. Got it? So if we have a solid section, these look like this. We have a solid approach. If we have a lumped section, this is like a typical floor beam. What happens is when we have a lot of aircraft structures are very lightweight, and so our webs are often so thin that they will buckle at a very low load. So even though they have area, they act as if they don't have axial area because they buckle so easily. But they are good at carrying shear. So we come up with what we call a lumped assumption, where we assume that flanges carry all axial load. They are the only things with area for resisting axial load. And thin webs carry only shear loads. This greatly simplifies our analysis. It is important you spend enough time understanding this method of analysis so you don't flub that up, but it's actually a simplified form of analysis. Okay? And we're going to be seeing this increasingly throughout 326, through our Structures 1 class. We'll also see it in our Structures 2 class. We see this same lumped assumption when we're analyzing fuselages, where the stringers act like lump areas and the skin basically carries, although it does carry Hooke and longitudinal stresses, because it buckles out of low compression stress, we often treat that like the lump structure as well. Wing sections are also handled like this quite frequently, and here are some other typical kinds of sections we might run into, where these are no longer solid sections. When we're doing bending analysis, we will ignore the webs other than providing shear continuity, which we'll learn about later, and our areas are all carried at these lumped, our normal loads are carried at these lumped areas. If we have a lumped section, for example, this one, then what we find is we can actually analyze this. Instead of putting in our widths and our heights of the elements, we'll just put in the areas of the elements and the y positions of those elements. And that makes our table construction a little easier. So in this particular case, let's say if this W is 1 inch and this height is 3 inches, then that means we've got 4 lumped areas and we're going to ignore our webs. That means let's say all of our areas are 1 square inch, so that would be 1, 1, 1, 1. And then our position of element 1 is at 0, 3. B is at 1, 3. C is going to be 0, 0, and 1D will be at 1 inch, 3 inches. We calculate the sum of the areas by summing these guys. That goes here. We multiply our area times the y bar. That goes here. Then we sum that up and divide this by this. That gives us the y bar. We take the area times the y minus y bar squared. That gives you this column. And because this is a lumped infinitesimal area, there's no 1/12 pH cubed term. So this is the total moment of inertia of the section about the horizontal x-axis. Now for these kind of sections, we have a simplifying thing that we now can calculate. Since the position of these flanges is the only place that can carry axial stress, we can just calculate our stress as my minus y bar over I. And that will, this is using a right-hand rule coordinate system. As long as our right-hand rule coordinate system, then this will give us a correct sign convention. Got it? Okay. If we have properties about 2 axes for a lumped section, for example, let's say we have a cross section like this. Let's say there's a wing segment. It's got thin webs like this. And we've got, say, 4 lumped areas. Since we've got a lumped assumption, we're going to ignore our webs and only analyze our area. Let's say this is 2 square inches, 1 square inch, 2 square inches, 1 square inch. That means that if this is this is A, B, C, D, A, B, C, D, then area 1, this is 2 square inches, 1 square inch, 1 square inch, 2 square inches. This one, if we define x and y from this point, then actually A is at 0, and let's say this is 10 inches. Let's say this is 20 inches. A is at 0, 10. B is at 20, 10. C is at 20, 0, and D is at 0, 0. We multiply A times X, and so on. A times Y, sum this column, sum this column. This over this is X bar. This over this is Y bar. Summation of this is A. Now we take the area times the y minus y bar, and that gives us this. Sum those up. That's the moment of inertia about the x-axis. Take the area times the x minus x bar. Sum those up. That's the moment of inertia about the y-axis. We then can calculate our stresses using right-hand rule. Since this was x and this was y, right-hand rule says that's positive, and this is positive, and this will calculate our stresses on any of those flanges. Got it? Now, if we have a composite section like this, we actually have a couple options. Option 1 is to just break it up and evaluate it. So if we call this 1, and then we call this 2, 3, 4, 5, 6, we would now have a table of 1, 2, 3, 4, 5, 6 elements. We put in the widths and the heights of each and the x bar and the y bar of each into our table and calculate our properties. Another way to do this, let's say we already analyzed this and we already know the properties of the z section. In that case, we can say, well, let's call 1 our z section and 2 our strap. We could put in the width and the height, and let's just say we're bending about one axis, the y bar, and the area, the ay bar, the ay minus y bar squared term, and the I term, which is 1 to bh cubed. Now in this case, for element 1, we don't need to put this in because we already just need the y bar, the area, and the I of the thing. And then we can calculate the ay of the thing and the ay minus y bar of the thing. For the second one, we have the strap. We just put in the width and the height. Width and the height. We then put in the y bar of that, which from here is going to go to, if this is h, it would be h plus t over 2. Calculate the area, and then calculate all this. And now we can calculate our new centroid by taking the sum of these over the sum of these. That's our y bar of the new section. And our I will be the summation of these two columns added together. Okay? So that's how we do that. I'm going to clean this up. Okay. One other idea here. Now we know our little standard formula here is MC over I, but it's also common to use what's called the section modulus. The section modulus is defined as I over C, and when we use this we can say that the moment or the stress is just M over the section modulus, where section modulus I over C. You'll see that's just combining these two terms into a new parameter S. This is used commonly with civils because they like to use a lot of cookbook lookup properties for different size beams and steel shapes and things. Used less commonly in mechanical and aerospace, but you should be aware of it. All right. Now, once again, if we have a lumped section kind of idealization with this moment applied, let's say we have a typical floor beam with vertical stiffeners located every so many inches, every W inches, and the distance between the centroids of our caps is about H, often 8 or 10 inches. If we pretend that this is a lumped section, that means we're going to pretty much ignore the skin for purposes of carrying axial load. We'll carry all the bending moment as a couple between these two caps. Okay? That means we can draw an exploded, that means this is what we see. We actually have two caps with this bending moment applied like this. We can calculate our properties as we see there. And what we're going to get is we're going to find that actually our force in the caps is just M over H, because we can just take a free body diagram about that bottom piece. we see that each stringer, each cap, is seeing an axial load change from one end to the other. The web is going to carry all the shear in the beam. We actually aren't ready to get too deep into this, but this is introducing some nomenclature that we'll be using later for lightweight beams like this. Especially, we'll look at this in 3271. Okay? Okay, if we have an aircraft frame, let's look at an example now. Let's say we have an aircraft frame, let's say it's dimensioned like this. You'll notice that the shear tie here is shown with a phantom line because a shear tie is discrete, it's not continuous, so it's not useful for carrying axial load. It just provides shear continuity between the skin and the stringer. What that means for us is we're going to ignore this when we're calculating properties. So we're going to need to calculate the properties of our frame, and we're going to need to calculate the properties of the skin. And we notice that that shear tie just tells us that they have shear continuity, so we can treat these all as a single section rather than two sections. And we're going to try and calculate the stress at a bunch of points. So in order to do this, we're going to first construct our table. This is our little element. We're going to number our little elements like this, and we're going to dimension them. You'll notice here, let's go ahead and take a look. What this means is our first element, you'll notice, is defined like this, where it is 0.1 by 0.5 inch, and it's located, if you say, well, it's from the bottom here, since this is our y and this is our x, that means its y bar is at 1.5 plus 5 inches minus 0.5 over 2. That's where it's located. Element 2 is defined like this. You'll notice it's 1 inch minus the thickness minus another thickness, so it's 1 inch minus 0.2, which means it's 0.8 inches wide, it's 0.1 inches tall, and now it's 1.5 plus 5 minus 0.05, which is 6.45 from the bottom. Our third element goes from here down to here. That looks like it is 5 inches tall, 0.1 inches wide, and it's located at 1.5 plus 5 over 2. Our next element is here, 4, goes from there to there. That means it's 1.25 inches tall, 0.1 inches wide, and its y bar is at 1.5 plus 1.25 over 2. Our next element, 5, is this little piece. We're going to break it up right there. That means it's 1 minus 0.1 minus 0.1, which is 0.8. It's 0.1 inches tall. It's located at 1.5 plus t over 2. Our next element, 6, is right here. It looks like it's 0.1 by 0.5, and it's located at 1.5 plus 0.5 over 2. And then we have our last element is the skin, which looks like it's 3.75 inches wide. And from the bottom, it's half of that. It's 0.08 inches tall and half of that height wide. Now we've constructed our table. You'll notice we've identified our elements and identified. Now, if this was if we had bending about two properties, we'd also need an x bar in this table. But since we're only bending about a single axis, we only need the y bar column. Calculate the a's. That's just the second column times the third column. Calculate ay, which is just the a column times the y column. We now can calculate the area, which is shown here already, and the y bar, which is ay over a. Once we have that, we can now calculate the a times y minus y bar column and the 112bh cubed column. And that allows us to calculate our I. The stresses we wanted them at a bunch of points at A, B, C, D, E, and F. And since we only have bending about one axis, all we need is the y position of those points. We see that point A is up here at 6.5. Point B is also at 6.5. Point C is at 1.5 from the bottom. D is in, and so on. So we can just plug into our formula, and that will give us the stress. This is going to be, we take our MC over I formula, or my minus y bar formula, and that will calculate the stress at each point. You can verify these numbers in the table here. Okay? Now if we have a lumped section like this one, we see we have two elements. We're going to ignore the web, plug in our two areas into our table, calculate our properties. You're starting to get the hang of this? And then we calculate our stresses. And if we wanted to, because this is a lumped section, it's very easy to now turn those stresses into forces by just multiplying each stress by its corresponding area. Okay? Once again, this is our lumped assumption for beams, and we can actually break this up with this kind of exploded free body diagram. This is actually getting a little ahead of ourselves. We're going to do more of this in 3.2.7.1. I don't think we're going to do a lot of that the rest of this lecture. Here's a little beam with a load. We see this looks like a lumped assumption where we're going to have two areas, one for each cap, and a web. We can see the max bending moment is going to be at AB, and that's going to be P times W, right, or times the length there. Calculate our section properties. And this is how we might draw an exploded free body diagram for this. Okay? Here's another example. This is not, once again, we see we got four lumped areas. Calculate our properties. And that's all there is to it. Okay, here's another lumped section. Once again, we now have more prop points, but we just put in our areas, we put in our y bars, and we calculate our properties. And then stresses, and then forces. Got it? You should have learned these approximations for thin-walled sections when you were in statics, but if not, here it is. If we have a hollow circular section, these are our properties. We've used these already when we covered, well, I guess not, because we covered torsion, not bending. These are the area and the I for a circular hollow section. And if it's thin like this, we can use these approximations. The area is 2 pi r times t, and the I is pi r cubed t. These are very useful for giving approximate properties, a little easier to calculate. This is a typical fuselage section. We can make a lumped set of properties where we analyze, put in the position of each of these stringers and the thickness of our skin. You should have learned to do that if you took statics at Cal Poly. You should have learned to do that as well. Okay. One other little idea, we've been learning about strain energy along the way, and if we have strain energy for bending moments, it's going to be calculated in the same manner. We're going to start off with our basic work energy relation that we've seen a few times now. We're going to call our relation for bending stress. We plug that in. We can plug that in like this. We then can simplify that a bit. Looks like that is the moment of inertia, so we can change that out and write it in that form. The strain energy is just the summation of the m squared dx over 2ei. If it's a constant section, then that integration just means you're going to change that dx to an L. It will be m squared L over 2ei. If it's continuously changing, you'll have to integrate it. If it's a lumped section, you can take the length of each little subpart and use the I for that, or the moment in that, as we've done before. Section modulus, we learned about this. Remember this? It's just I over C. What is the best way to idealize this puppy for computing properties? If you think about this, you'll notice that any of these methods will work. Now we start doing plastic bending next semester, we'll find out that some of these methods are better than others for doing that kind of calculation. But for our purposes, any of these four are fine. This is another foundational lecture with basic building block concepts that you need if you plan to do any structural analysis in industry. You should be able to do P over A, whether it's normal or shear, TR over J, TT over J, and now we've learned about MC over I and how to calculate that for bending about one axis or about two axes or even combining with axial load. These ideas are critical, and it's very important that you take the time to master this material. Once you've done that, you can move on as we learn about multiple section properties within the same section, and then we start looking at deflections. Enjoy.